Now let's talk about numbers that can have a non-zero fractional part, so real numbers, and we'll talk about these in the context of literals, numbers we enter directly into our code, and these real numbers are known as floats. As an example, 314.1592 is a literal float, and when we hit return, the value is just echoed back to us as before. And some comments on this, that real numbers are known as floats, and if a number, a literal, has a decimal point, it's a float. Okay, no ifs, ands, or buts about it. So it doesn't matter if the fractional part is 0 or not. If that decimal point is present, it's a float. And we'll see that in a bit. Also, floats, unlike integer values, have a finite size and finite precision. And this is a consequence of the way they are stored in the computer. Typically, we're using 64 binary digits to store the float number, and there's a limit on what we could store in 64 binary digits. And what this translates into is about 16 decimal digits of precision. We mentioned before that ints are stored exactly, but in contrast, floats in general, even if they're not bumping up against that size or precision limit, are stored only approximately. So in general, they are approximate, and we won't get into all the details of that, but we'll talk about that a little bit. Now, ints and floats quite often can be used together or in similar expressions, but there are things that we can do with integers that we can't do with floats, and some things we could do with floats and not ints. So for now, we just want to be sure that we recognize which is which when it comes to ints and floats. So here are some other examples of floats. We could say have minus 0.1234. That's a float. How about if we had minus and then just write the decimal point 1, 2, 3, 4? Well, that's still a float, and notice what is echoed back to us doesn't look exactly like what we typed in. The interpreter added the leading 0 for us. Here's another float, 234.000001. And how about if we have 234.0? Well, the fact that that decimal point is there makes this a float. When we hit return, we're seeing that float value. But how about if we just wrote 234 point and didn't write anything beyond the decimal point? When we hit return, the value that's echoed back to us again doesn't look exactly like what we typed in. The trailing 0 to the right of the decimal point is added, but this is again a float value. It should be no surprise that float literals can be arguments for the print function. So we could have 234, and let's give it some non-zero fractional part, and that's just echoed back to us. Let's add a few more digits here, and here we're seeing a consequence of the finite precision. What appears at the end of that number isn't exactly what we had entered, because we only have about 16 digits of precision. When writing float literals, we can use exponential notation. And the way in which we do so is the way it's done on most calculators. So you're probably familiar with this. If we write a number such as 3.14 and then E2, that E means exponent, and the 2 is the exponent for the number 10. So this is equal to 3.14, then times, and I'll use the asterisk to mean times, 10 raised to the second power, raised to that 2, so that would be 100, or essentially this is equivalent to 314.0. And in general, we can write that with this exponential notation, I'll just use the generic x to mean some digit. We could have x point xxx. This could be positive or negative. Then the letter E, it could be lowercase or uppercase, and then y. And that can also be positive or negative. And this is equal to x point xxx times 10 raised to the y power. So some examples of this, if we have 2.E1, well, that's the number 2. We don't have anything beyond that decimal point, and we're saying this is multiplied by 10 raised to the first power, so this should be 20, and it is. If we have minus 1.75, and then E, and how about a minus 3 here? So this is negative 1.75 times 10 to the minus 3, so that's 1/1000th, and there's the result. How about this? If we have 3E0. Now, I said before, if a number has a decimal point in it, it is automatically a float. But if we use exponential notation, whether that decimal point is present or not, it's also a float. So this is a float. And hitting return, we just get 3.0. Recall that we said that integers are stored exactly, so we can have a very large integer, such as this. When I hit return, that integer is just echoed back to us exactly as we typed it in. I'm going to recall that number now and put a decimal point at the end so that it will become a float. So it is a float. And when we hit return now, what is echoed back to us is no longer exactly what we typed in. There are about 16 digits of precision here, and beyond that 16th digit, everything else, all that precision, is lost. So we see we have a number that's 4.7 times 10 to the 43rd, but it's an approximate number. Now I'm going to enter a really large number consisting of just the digit 4 repeated multiple times. So I'll paste this in. Let's leave it as an int. If I hit return, that big number is just echoed back to us. I'm going to recall that with the keyboard shortcut. I will put a decimal point at the end so it becomes a float. Hitting return, we see that that's about 4.4 with lots of other 4s times 10 to the 307th power. So it's a really big number stored with finite precision. I'm going to recall it again, and now I'm going to add another 4 and hit return. So just added one more 4 to this. And hitting return now, it says, oh, that's infinity. That's bigger than I can handle. So this is demonstrating the finite size. Now our biggest number can be about something times 10 to the 307th power. Beyond that, we've overflowed what Python is capable of storing. One thing that I should probably mention here is this really large number that is just a bunch of 4s is really one number, but the interpreter, once we get to the end of the line with these really big numbers, it will wrap the number around to the next line. So here I'm just pounding on the keyboard some numbers, and we can see when I get to the end of the line, add another digit, we start entering the value onto the next line.